be talking about the handling of structures in dependent type theory and in Lean and Mathlib in particular. And so I won't be talking so much about my own work as about Lean and Mathlib in general. But just by way of background, I'd like to point out that as recently as 2017, there were very few mathematicians using proof assistants. So now it's very remarkable to me that so many mathematicians have embraced Lean. And I often wonder, why Lean in particular. I mean, some of the answers are that it's a well-designed system, and it was written with both mathematicians and computer scientists in mind. So when Leo Demora, first started working on Lean, he certainly had the software community in mind. But I was involved in developing some of the early libraries, as were people like Floris Van Doorn and Rob Lewis. And we were interested in formalizing mathematics. And Leo was very attentive to that. And so made sure that the system, accommodated our desires. Similarly, I wrote some of the early documentation, and my training is as a mathematician. So in writing the documentation, I was, trying to explain to colleagues how formalization works, and that seems to have gone over well. Early on, some very enthusiastic mathematicians and very good mathematicians got involved. So people like Kevin Buzzard in 2017 started using Lean and blogging about it, and people like Sebastian Guzel and Patrick Massot and Johan Komelin. And there quickly formed an online community around Lean that was good about promoting it. And also Mario Carnero was involved early on. He was the one who first broke off Mathlib from the core Lean development and turned it into an open source project. And he was there around the clock supporting, mathematicians and helping them learn how to formalize and write good formal code. But most of these, reasons seem kind of like historical accidents. I think at the core, the two things that make Lean really good for formalizing mathematics are, first of all, that it has good support for classical mathematical reasoning, and second of all, that it has good support for reasoning about structures. And systems like Isabelle and Hall-Light, meet the first requirement. They're resolutely classical and designed for classical reasoning. But systems like Coq and Agda are better equipped to do algebraic reasoning. And both of these, I think, are essential to mathematics. And so I'll try to make that case. So just as far as the first about classical mathematical reasoning, I don't want to say too much about it. But so for example, in Lean, you can define the factorial function from the natural numbers, and it's then a computable object. So you can evaluate it, right away. You can, extract a binary and run it. So Lean is quite a good programming language, and you can use it to write programs and reason about them. So it's, it can be as computational as you want it to be, but you don't have to be, right? So just as easily in Lean, you can define the function from reals to reals, the step function, which is 0 when x is less than or equal to 0, and then jumps up to 1. Or you can define the function that's, 1 if x is irrational and 0 otherwise. And you can just do it and and reason about it and prove things about these. And it's not that you can't do this in a system like Coq or Agda as well. But they seem to be discouraged there. It just seems to be counter to the aesthetic of the community. In the late 19th century, the mathematical community made a choice that to separate computational reasoning from reasoning about abstract concepts. So mathematically speaking, what you do is you define the real numbers. You can characterize the real numbers up to isomorphism in lots of different ways. And once you have that characterization, you want to reason about the reals abstractly. You want to reason about arbitrary functions from the real numbers to the real numbers. You can then restrict attention to continuous functions or measurable functions or any class you want. But all that is separated from the fact of computationally how you represent real numbers and how you compute with them. And I think that's important. And so any proof assistant that tries to force mathematicians to think computationally, I think kind of rubs mathematicians the wrong way. But what I want to talk about today is structural reasoning, the mechanisms that Lean and Mathlib afford for reasoning about axiomatically characterized structures. which since the early 1900s have really been central to mathematics. And nowadays you can calculate with structures as easily as you can calculate with numbers, which is to say you can do things like take products of structures and powers and limits and build quotients and so on. Right, and I've used these terms because these are all things that you do with numbers. You multiply numbers and take powers of numbers and so on. And the point is, anything, the kinds of things that you can do with numbers, you can do with structures, but then reason about elements of those structures as well. And so that says that you really, structures have to be treated on the same level as mathematical objects like numbers, right? And any foundation that doesn't do that is just kind of at odds with mathematical thinking today. Um, so this rules out simple type theory as an attractive option, because in simple type theory, you have one language with which you define your types. And then only after you define your types can you start defining mathematical objects of those types. So you can't go back and forth. Set theory is an alternative, and indeed, set theory was designed for just that reason. You want to have everything be a set. Everything is on par. Everything is on the same level. So you can define structures and numbers, and at the core, everything is a set. But type theory does a lot of work for you. So having types around lets you overload notation and leave a lot of information implicit. And having a type discipline means that the system can infer information. And it lets the system provide better error messages and information about what you're doing. And so just to clarify, I mean, it's certainly the case that with enough work, you can make any foundational framework. You can do anything you want in any foundational framework, which is to say, you can always add axioms to simple type theory to give it the same strength and then interpret things back and forth. So, up to translation, the systems are equivalent. But it's just the practical question of well, again, getting it to work in practice. And there, I will make the claim that any practical solution will be at least as complicated as dependent type theory. The argument being that, as soon as you decide you want to use types are important, then you need types. And if you're going to do algebraic reasoning, the types have to depend on parameters. And then, then you're doing some kind of dependent type theory. So I'd like to read you a quote from Sebastian Guzel's webpage. I'm not sure when he wrote it. I quoted it as early as 2019 in a talk. It's still on his webpage now. I'm guessing he wrote it probably around 2018. But the quote is, out of curiosity, I've given a try to several proof assistants, i.e. computer programs on which one can formalize and check mathematical proofs from the most basic statements, definition of the real numbers, say, to the most advanced ones, hopefully including current research in a near or distant future. So remember, he's writing this in 2018. The first one I've managed to use efficiently is Isabelle Hall. In addition to several facts that have been added to the main library, for instance, conditional expectations, I have developed the following theories. And he gives a list of theories that he's done in Isabelle. But then he goes on to say, I've been stuck somewhat by the limitations of the underlying logic in Isabelle, the lack of dependent types, making it hard, for instance, to define the p-adic numbers, as this should be a type depending on an integer parameter p, and essentially impossible to define the Gromov-Hausdorff distance between compact metric spaces without redefining everything on metric spaces from scratch and avoiding type classes. These limitations are also what makes Isabelle Hall simple enough to provide much better automation than any other proof assistant. But still, I decided to turn to a more recent system, Lean, which is less mature, has less libraries and less automation, but where the underlying logic, essentially the same as Coq, is stronger, and as far as I can see, strong enough to speak in a comfortable way about all mathematical objects I'm interested in. So I like this quote. I think Sebastian is speaking, for the mathematical community when he's really highlighting the importance of being able to do structural reasoning in a proof assistant. Okay, so that's what this talk is about today. I want to talk about Lean's handling of structures, and I've classified it as the good, the bad, and the ugly. So the good news is that Lean and Mathlib support an extensive network of structures. So it's working, it succeeds. The bad is that the complexity of this network of structures poses challenges for the library, the development of library and the maintenance of the library. And the ugly is that it also poses challenges for automation. So So I think I have way too many slides that to fit in this um, to use today. So the slides are already on my webpage, so we'll see how far I get. But this is at least what I have slides for. The title, The Good, the Bad, and the Ugly, is taken from a 1966 spaghetti western, so a cowboy movie directed by the Italian director Sergio Leone. And so as long as I have a reference to pop culture, I decided to put another one on this slide as well. So structural reasoning is one of the sources of the impressive power of modern mathematical reasoning. It's what makes modern mathematical reasoning what it is. But as the Spider-Man comics and the Marvel franchise tells us, with great power, there must also come great responsibility. So if you're going to do algebraic and structural reasoning, you have to do it right. So mathematicians have to learn how to do it and learn how to do it right. And if you're going to do it in a proof assistant, you have to support all the things that mathematicians want to do. Okay. And so I like to inject a bit of history into a talk. And I don't know how interactive we can be, but we'll try it. But here's a quiz. So it's anybody who first gave the axiomatic characterization of a group? I think you have to.
Can you hear what's that in the room?
If you say it loudly, I can hear it.
So I think we had Galois.
Galois. So Galois, no, he defined a particular one, groups of substitutions, but just as a group, as an operation with an identity and inverses and so on. That was first done by Cayley in 1854. The paper didn't get much traction. In 1870, Kronecker gave a paper where he gave an axiomatic characterization of abelian groups and showed that they're useful in number theory. So that's 1870. Quotient groups. So quotient groups, so it's kind of funny. Jordan in 1860 had a general notion of a quotient group, but the idea is that a quotient group is something like a group, except you replace equality by an equivalence relation. Right? So this idea of modding out of by the equivalence relation, wasn't there yet. There were particular constructions. So in fact, Dedekind in lectures on Galois theory in the 1850s had done that construction. And in 1872, he did a similar construction. But it wasn't until Holder in 1889 that you had the modern notion of using equivalence classes as the objects of a new group. Ideals in a ring? Anyone?
Dedekind, right?
Yeah, Dedekind. So in 1872, he did it for groups of the rings of algebraic integers. But quickly it was generalized, and so the Riemann-Roch theorem in 1882 with Weber, he is using ideals in rings of functions. Modern definition of a Riemann surface. Right. So Riemann in 1851 dissertation, he has the beginnings of the notion, but kind of something like the modern notion. So that doesn't happen until 1913. Weil wrote an influential book on the notion of a Riemann surface. Topological space.
It's tricky.
So Hausdorff, 1914. Let's see, a Hilbert space. It's the obvious guesses. So I mean, around the 1900s, I mean, Hilbert and Schmidt and Riesz, they were doing studies of integral equations, so they were using particular Hilbert spaces. But the characterization of a Hilbert space as a complete inner product space. So the author called this an abstract Hilbert space. And so who was that? Any guesses there? So think.
Von Neumann, maybe?
Von Neumann, yeah, von Neumann in 1929. Good. The modern definition of a measure on a space as a sigma additive function. You have a sigma algebra and a sigma additive function on that.
There's
So
Lebesgue
again,
in the chat.
yeah, so the names you know of like Borel and Lebesgue and Karateadori, they were dealing with measures as early as the 1900s. But the axiomatic characterization, so if you think the application of probability, Kolmogorov, 1930s, that happened in 1930s. Okay. And the p-adic integers,
File.
that's Hensel. Hensel,
That's good.
1897, started using the p-adic integers.
Yeah.
Okay, so the messages here is that we're talking about all of these things come into mathematics late 1800s, early 1900s. And another point to get across is very often first, the concrete instances come in first. And then people, decide that it's useful to give the abstract algebraic characterization. And so, going into the 1930s, 1940s, structuralism on the rise. That it's becoming clear that it's useful to mathematics to give the axiomatic characterizations of the structures and reason about them in those terms. Okay, so here I just want to give some examples of how things look in Mathlib. And so I start with something just very concrete. I mean, quadratic reciprocity. So if P and Q are distinct odd primes, then the Legendre symbol of Q and P times the Legendre symbol times P of P and Q is -1 to the P over 2 times Q over 2. And the Legendre symbol is, is 1 if of P and Q is 1 if P is a quadratic residue mod Q and, -1 otherwise. So the thing to notice that in Mathlib, quadratic reciprocity is stated in terms of the Legendre symbol. And the Legendre symbol is defined in terms of quadratic characters. But here, quadratic characters is, defined in this generality. It makes sense for any monoid with 0. Right? To just write down the definition, if A is 0, then 0, else if A is a square, then 1, else -1. Well, all you need is a 0. I guess you need a 0, a 1. Sorry, no, so you just need a 0 and a multiplication, which is, so how the definition is cast. And so, which means that, I mean, quadratic reciprocity was initially stated in elementary terms, but at some point somebody found it useful to go back and refactor the library and introduce this abstraction monoid with 0 and then rewrite these definitions. So, when you define the Legendre symbol, you need that the integers modulo P is an instant, well, it's an instance of a lot of things. It's a ring. If P is a prime, it's a field, but it's also a monoid with 0, which means you can make sense of this definition. Here are the p-adics. So if P is a prime, you have the p-adic norm on the rationals, and then the p-adics are just the Cauchy completion of the rationals with respect to the p-adic norm. And again, you're supposed to notice that, so this is a construction of a data type, and a data type that has the structure of a metric space and other things, other structures on it, right? But it depends on a parameter P. You start with a number and you construct a norm, and then you construct a metric space out of that. And then you can define the p-adic integers, or those are the p-adic. So you introduce the notation QP for the p-adic numbers. The p-adic integers are the p-adic numbers with norm less than or equal to 1. And then, Hensel's lemma is a fundamental theorem that gives a criterion that guarantees the existence of solutions to a polynomial. And, it's stated for polynomials over the p-adic integers, which is, again, has algebraic structure. It's a ring. You have all the polynomial operations you can add and multiply polynomials and so on. And so, again, you're just constructing algebraic structures. They depend on, in this case, a parameter P, and then you can use them. Here are a couple more examples. So I was amused to find that the free abelian group is defined like the first definition of the first line there. I mean, they're more obvious, concrete representations of the free abelian group on a type alpha. But there's the Mathlib has the construction for the free group, and it has a construction that will give you the abelianization of any group. So you take the free group and you take its abelianization. But then by default in Mathlib, groups are written multiplicatively, but the free abelian group you want it written additively. So additive just converts it to additive notation. Similarly, there's the first Sylow theorem. So you say what a P group is, and the first Sylow theorem says that every P group is contained in a Sylow P subgroup. Again, this less than or equal, there's some structural stuff going on there. So Mathlib recognizes that the subgroups of a group form a lattice. So this is less than or equal in the lattice structure. Just do a couple more examples. So here's a nice example, the finiteness of the class group. So the comment tells you what the theorem says. So the main theorem is that the class group of an integral closure S of R and a finite extension L of K, which is the fraction field of R, is finite if there's an admissible absolute value. And the remarkable thing is that all this above is the boilerplate that you need just to just to state this. So you've got R and S with some rings. So S is a commutative ring. So it's an integral domain. So it's a commutative ring, which is a domain. R is a Euclidean domain. You've got some fields, some algebras, extension. You have to say that things are extensions. So all of this is kind of structural, boilerplate that's needed to talk about the fineness of the class group. But it just happens in Mathlib. This is that people do it and it works. And just to take one more example from measure theory, this is Egorov's theorem that says if you have a sequence of functions that converges pointwise almost everywhere, then you can throw away an arbitrarily small set and then get uniform convergence. And again, your sequence is F. So F is indexed, an index sequence of functions from alpha to beta. So alpha, is a measure space, and with a measure, to talk about convergence of functions, beta has to be a metric space. But then even, in textbooks, Egorov's theorem is usually stated for, for sequences of functions indexed by the natural numbers. But whoever wrote this realized, oh, you can be more general than that. So in fact, all you need is kind of a countable index that's an upper semi-lattice, right? You need kind of just a net. And so it's stated in that generality in Mathlib. Okay, so these are just examples of and to any computer scientists in the room, or in the audience online, I want to emphasize that I'm not going through Mathlib and kind of cherry picking the kind of extreme examples. I mean, this is what Mathlib looks like, and this is what modern mathematics looks like. Everything, as I indicated with the historical prelude, everything here has been around for a century or more. And it's all absolutely fundamental to mathematics. If you're doing number theory, if you're doing analysis, you're doing things like this. So again, if you want to proof the system for modern mathematics, you have to be able to do things like I've just shown you. Okay, so I think I can pause and see if, let me pause and see if there are any questions. So I think what I was going to do now is just talk about the nuts and bolts of how things are done in Lean and Mathlib, how structures are encoded. Before I do, let me pause and ask, are there any questions?
There seem to be no questions right now in the room. Are there any questions by people joining online?
I would actually like to ask a question. Hi, Jeremy, this is Marco.
Hey, Marco.
I was wondering if you think that these systems are well suited also to do calculations in a certain possibly abstract algebra. So instead of trying to, I don't know, get some Python code up, where you encode the rules of the algebra and then try to do computations for given examples, would you think that formalizing them in Lean in this structural language gives you an advantage to handle these calculations because you have all these extra layers of abstraction?
So again, tell me what kinds of calculations you have in mind?
One example that I have in mind is like a strand algebra. So typically you'd have lots of graphical representations of strands and crossings, and you have matrices that you can multiply in a certain way that contain such strands.
Yeah, so again, I tend to think if it's mathematics, then Mathlib is a good place to do it. and moreover, even if there's a computational component, if it's mathematics with a computational component, still Mathlib is a good place to do it. And the things that can be done computationally should be able to be, you should be able to do computationally. Okay, so let me move on and say a little bit about, again, for people who are not familiar with Lean and its way of doing things. Let me just say a little bit about how it's done. So, almost at the axiomatic level in independent type theory, you can declare, in Lean's foundation, you can declare structures. So, the first declaration there declares point to be a structure with 3 components, X, Y, and Z. And then you can define, elements of those structures. So so a particular point, will have an X value and a Y value and a Z value. And so the first definition is one notation for it. But Lean gives you various, ways of notationally of writing, of defining elements of structures. So for example, the second one, the angle brackets are called anonymous constructors. If you know you're constructing a point, you can just give the fields and Lean can fill in the rest. But you define a point. The point is, if you have a point, you have an X and a Y and a Z. And you can define operations on points. So for example, to add 2 points, you take the components and add them and then put them back together. But so a nice thing about dependent type theory is that facts and data are handled almost, notationally the same way. So for example, you can define a structure that has not only X, Y, and Z, but also adds the constraints that X, Y, and Z are non-negative and sum to 1. And the definition looks almost the same, except that in addition to X, Y, and Z fields of type R, you also require these constraints, and they're labeled. And similarly, you can define operations now. So these are elements of the standard 2 simplex. They're triples X, Y, and Z of non-negative numbers that sum to 1. And you can define operations on those. So for example, the midpoint of 2 elements in the standard 2 simplex should again be such. So you define the X and the Y and the Z value. And then you're left to prove that the remaining constraints hold of the X, Y, and Z you've defined, from the fact that they hold in A and B. And so, in this way, you can use this idea to define structures. So for example, a group you can think of as a combination of data and axioms. So a group, there's a carrier type, and then there's a multiplication and a 1 and an inverse on the carrier. And they satisfy the usual group axioms. And you can declare them to be part of a structure in that way. And then in Lean, you could, declare, G to be a group, and then elements of the carrier of G. In Mathlib, this is not how things are usually done. So there is this notion of group is around, but the more common practice is to separate the type of the group from the group structure. Right. So the definition that's more commonly used in the library is to define the notion of a group structure on any type. So if alpha is a type, think of it as a parameter. Group on alpha consists of the multiplication of the 1 and the inverse satisfying those properties. And then, to reason about groups, you're reasoning about any type G with an associated group structure, and then elements G1 and G2 of the type. And so here, the curly brackets mean typically you don't want to mention G. You want to leave it implicit. You want to infer it from the context, for example, from the type of the elements G1 and G2. The square bracket notation also means that you don't want to typically give the group structure explicitly. You want Lean to infer it automatically. And in fact, you don't even want to have to name it. So that's why it's kind of anonymous. So the square brackets denote type class inference that will find the relevant group automatically. And so, when I explain to students, and so we do this in mathematics and Lean, when we try to explain students, all the mechanisms that Lean has for managing structures, what I like to do is kind of work backwards rather than saying, here are the mechanisms and here's how you use them. I like to think backward and think about all the things you need to do if you want to do mathematics, and then present, the mechanisms and Lean as a solution to that problem. Right. So I've argued that doing mathematics requires, defining algebraic structures and reasoning about them. So you want to define groups, rings, and fields, and reason about arbitrary groups, rings, and fields. But you also want to define instances of those structures. Right. So for example, you want to define the real numbers and recognize it as having an ordered field structure and the structure of a metric space and so on. You want to write things like X plus Y and not have to specify that this plus is the plus in the reals or the natural numbers or the integers or some abelian group or some ring and so on. you want to write f as continuous. For example, f is a function from the reals to the reals, and I have to specify the topology. But then there are algebraic and there are structural hierarchies, right? So, if you have a normed additive group, well, from the norm you have a metric, so you have a metric space, and every metric space is a topological space. And so, you need to sort of keep track of those relationships in mind. And you need to be able to define functions and operations on structures. So in the introduction, I gave examples like taking products, powers, and limits, and so on. And then as far as inheriting structure, I mean, things get even more complicated because you can, structures can inherit structure from, more specific and more general ones in various ways, right? So some structures extend others by adding more axioms, right? So if you have a commutative ring, in particular, you have a ring. If you have a Hausdorff topological space, in particular, you have a topological space. But some structures extend others by adding more data. So, for example, if you have a module in hand, you have an abelian group in hand, and hence a group, and so on. Okay. Or if you have a normed field, in particular, you have a norm, and you have one, and you have a field. And then some structures are defined in terms of others. So if you have a metric space, you have a topological space, even though in the usual characterizations, a metric space doesn't specify the topology. Okay, so there are various ways, there are various relationships you need to keep track of. Okay, so in Lean, we've seen that you can define a group structure on a type alpha by group alpha. And you can define instances the same way you define, points and instance of the standard 2 simplex. So for example, to define the permutation group on alpha, so you take the data type of permutations on alpha, and you just give the group the usual group structure. So the multiplication will be the composition of permutations. The one will be the name is kind of funny, but it's the identity permutation, and so on. Okay, so we can define structures, we can define instances, but then you also want to handle notation. So given 2 elements of the permutation group, you want to multiply them, you want to take the inverse, you want to use, I'm sorry, was there a question?
There was no question, I think.
Okay, I heard something, okay. So you want to have notation for algebraic structures, and then you want to do define notions. So in any group, for example, you can define exponentiation to any power, any natural number power, and even negative powers, or conjugation, right? And these notions you want to define generically in any group. And similarly, you want to apply theorems about arbitrary groups to the permutation group. So you want to state theorems that hold for any group and then instantiate them. And roughly, there are just a few simple components that make all this possible. So the first is just the general logic. So if you have a definition that makes sense in any group, well, you just define it parametrically as a definition over any group. So the group and the group structure are arguments to the definition. And similarly, a theorem about elements of an arbitrary group, quantifies over the type of the group in the structure. So for every type G, for every group structure on G, for all elements G1 and G2, and so on. Okay. But then, typically, to make it workable, you want to leave out the arguments for the type and the structure. So they're generally left implicit, which means that the system has to fill them in. And so then you have a system called type class inference that is supposed to do that. And so the idea is you register instance relations with the system, and the system uses the information to fill it in for you. Okay, so and this happens even for overloading of structures. So the way we overload the plus symbol is you can think of plus as working for any trivial structure that has a notion of addition, right? So we define a trivial structure, add. It's the structure of types that have just a binary operation that we're going to call add. And the add, the add function is parametric. For any type and anything that has an add structure, it extracts the binary operation, the addition. We define the notation plus to be that function. But typically, we want to leave the type and the structure implicit. So it really is just a binary operation. And then, so for example, we define addition for points, and we just then declare that as an instance. And what that means is, whenever we have 2 points, Lean can infer that. So it knows that it has to find an instance of the structure, of the add structure, and it can look it up. We declare that instance, and Lean can just find it. Okay, so the plus notation is shorthand for add PQ, but there are arguments implicit that are left here. And so the full adding the @ symbol in front says you want to display all the arguments explicitly. And so the addition is, depends on the type and the instance that is found. Okay. And so that's the idea. So the class command is just like defining a structure, but you register it with the system as a target for class inference. And then the instance command registers particular instances for type class inference. And okay, and I just want to give you statistics, but just to give you a sense of the complexity involved. Let's see. Oh, so for example, in these examples, you declare group to be a class, you declare the permutation group to be an instance. And from that moment on, you can use any theorem at all about groups or any notation for groups or any defined function for groups with the permutation group. So similarly, you declare the reals to be an instance of a ring. And from then on, you can use all the ring operations, ring definitions, ring notations for rings, and so on. Okay. And yeah, and again, so under the hood, when you say something, whenever you say plus, there's this implicit information you have to fill in. When you say that a function is continuous, implicitly, there's a topological space, there's a structure on the types, and Lean has to fill that in automatically. Right. And so just to give you an instance of that in action, if you have functions f and g from, r cross r to r, so pairs of real numbers to the reals. So Lean can infer what you mean by the addition. It knows that you have it can figure out that the addition is commutative. You can say that f is continuous, and again, underneath the hood, Lean has to figure out what the relevant topological spaces are. And here, if you ask Lean to explicitly print out all the information, you see that it's filled in the topology on r cross r with this funny thing. It's inferring that, oh, well, it's a product, so I want a product of 2 topologies. Then it's got to figure out what the implicit topology on R is. And it's getting that so it knows that the reals are an instance of a pseudometric space, and every pseudometric space is a uniform space, and every uniform space is a topological space. And it says, so now I know what it means for f to be continuous. And the amazing thing is that you don't have to see this. This just happens under the hood, and everything works. And so I guess I'll spend the last few minutes. I want to just give you a sense of the complexity of the hierarchy. So I'm going to ask you to guess how many classes, how many structures are declared in Mathlib. Right. So the hint is that there are about 1 million lines of code, 1 million lines of formal definition and proofs in Mathlib. So how many would you guess? How many classes are declared? So somebody somewhere has to be. I'm sorry, what?
1,000.
5,000.
5,000. Yeah, that's not a bad guess. I gave a talk at Rutgers, and I raised this question, and Alex Kotorovich immediately guessed 1,000, and I said, well, why 1,000? He said, oh, there's the square root law. So apparently there's this heuristic, some kind of square root law. So if there are 1 million lines of code, he guessed there should be 1,000 definitions. Anyhow, he wasn't too far off. 1,300, at least a few months ago when I looked at Mathlib and computed the statistics, there were about 1,300 classes and 22,110 instances. And let me just kind of show you, let me just kind of show you a little bit of what that looks like. So let's see. So one thing you can do, I mean, I'm not very good at this, but you can extract. So here's like a small piece of the hierarchy. And so, you can kind of move back and forth. And so here's just but you see there's a normed linear ordered field. There's a concept that. So every normed linear ordered field is a linear ordered field and a normed field, which is in turn is a field. And every field is a, well, I wonder where that's going back to. Let's see, going to the other side. Every field is a semi-field, which is a com group with 0, which is a com monoid with 0. And then there's in, vin, div, right? So this is a little piece, a small piece of the structural hierarchy in Lean's library. And here you see the notation class, the mul and 1, non-empty at the bottom. So here's a little picture of Lean's hierarchy. Another thing I can show you that you can do is kind of fun to do is, so the Lean documentation will give you information about the classes and so on. So for example, if you look up, so if you look up the reals, here's the structure reals, you can see all the instances that, structures that the reals are declared to be instance of. So every, the real numbers are an instance of, well, all these weird things in e-real, cam lift, and let's see if we can find something more common. So it's an instance of a commutative ring, right? The reals are an instance of a field. Yeah, there's somewhere we should have lattice. The reals are an instance of a lattice. They're an instance of a linear order, and so on. There is a redundancy here, right? So so every linear order is a lattice, and so on. So there is redundancy, but this isn't all the things that Mathlib knows the reals are an instance of. These are just the instances that are declared, right? For all the things that that can be inferred from these are additional things that the reals are instances of, right? So it's a pretty substantial list. So this says, given a structure, you can go to the documentation and look up the instances that are declared for it. Going the other way, given a class, you can look at some of the instances of it. So for the class ring, so first of all, the axioms will look a little bit weird because, well, there's some things that look familiar, like 0 plus a equals a, and so on. There's stuff added into the definition of a ring structure, which might look strange, but I won't talk about that now. But you can look at, some of the things that are declared to be instances of rings. So for example, the matrix, so if you have matrices over a ring, have a ring structure. Let's see. Yeah, so there are various constructions that give you rings. Again, these aren't the only things that give you rings. I mean, if you have a field, you have a ring. So anything that's an instance of field is an instance of ring, and so on. So these are the ones that are just directly declared. But there are a lot of them, and Lean has to manage them all. Okay, so let me head towards wrapping up. So just say a little bit more. So I mean, there are all these classes. Again, if you want to make sense of them, some are classes that are there just to handle overloaded notation. So we saw 1 and mul, and there's add and inv and so on. They're the usual algebraic structures, groups, rings, fields, lattices, modules, all the things that you're familiar with. There's some things that are there that are useful for computational purposes. It's useful to know when types are not empty, when you can pick a default element, when relations have computational, can be cited computationally. There are some classes that usually aren't used on their own, but kind of added on to other things. So for example, if you want to have a non-trivial ring, there's kind of a class for rings that says that the 1 is not equal to the 0. It's just kind of an add-on. And then there are these kind of weird generalizations, like before I showed you monoid with 0. Now there's group with 0. That as you develop the library, you just keep finding yourself wanting to break out pieces and generalize because things come up, more than once.
Sorry, there mix in.
So by a mix-in, yeah, I mean, I just mean something that it's not intended. You wouldn't say that alpha is a less distrib class, but you might say that it's a ring. Well, yeah, it's a ring and then has this extra property, right? So in other words, if you have, well, I guess rings are distributive. So in other words, if you have an algebraic structure and you want to add some extra axioms to it, I mean, good examples for topological spaces, like the separation axiom, saying that it's, Hausdorff or T1 or, regular and so on. You don't create a structure, Hausdorff topological space. You have a structure for topological space, and then you have additional classes that add the extra structure to it. Okay. I think so. I mean, other things I would have talked about that are in the slides are some of the challenges, some of the problems that arise, and then some of the challenges for automation. But let me just jump to, so they're in the slides. Let me just jump to the conclusion, which is that, so I mean, as I've argued, structural reasoning is one of the most salient and powerful features of modern mathematics. It's one of the things that makes mathematics what it is. And so, if you want to have a proof assistant for mathematics, you have to support it and support it well. And it's not easy. The complexity of what the system has to do, all the things that the system has to do every time you write a plus symbol, or every time you say, this addition is commutative, it's got to figure out, why that's true. So it's to me, it's just one of the most striking things about Lean and Mathlib is that they function at that level of complexity as well as they do. But we're not out of the woods yet. I mean, at the outer limits, the complexity does pose challenges for the development of the library and for maintenance. At the outer fringes, we're hitting performance problems. We're hitting problems where just things don't work smoothly. And it also makes automation more challenging. And so I think it's an ongoing process. We're not there yet, but we're making good progress on the problem. Okay, thank you very much.
Thank you very much for your talk, Jeremy. Are there any questions here in the audience?
Yeah. Hi, can you hear me?
I can.
I was wondering how the system handles conflicts between different possible interpretations.
Yeah. So one of the things that's in the slides that I did not have time to talk about are diamond problems. So this is when for example, you write continuous, and the system has to infer that there's a topological space, and there may be more than one way that it can be done. There's kind of a hierarchy of badness. There are diamond problems where, so there are sometimes that it can infer the relevant object in two different ways, but it's not a problem because Lean can recognize them as being the same. Okay, and so that's fairly common, and that's okay. There are, I guess, at the other extreme, there are times when mathematically it's referring two different things, and they're just really different, and that's just a mathematical mistake. You've kind of assigned two different, for example, topological spaces as the canonical topological space on a structure, and if they're not the same, then there's just confusion in your library. But then there's the more interesting problem when you can infer the relevant object, say a topological space, in two different ways that are not obviously the same. They're not syntactically the same. Lean can't recognize that definitionally, but mathematically they're provably the same. And when that happens, so this is a diamond problem that you need to do something about. And in the library, there are various mechanisms for handling it. And I think it'll take me too far afield to start describing them. But if you look at the slides, so they are discussed in the textbook, the online textbook that I wrote with Patrick Massot, Mathematics and Lean. There's a chapter where there's a discussion of diamond problems. And on the slides, there's reference to a couple of papers in the literature. So this is a problem that's actively studied in the literature. But yeah, so hunting down diamonds is it's a hobby, it's a pursuit, it's something that people do, that people who are developing Mathlib do routinely, and apparently they crop up in mathematically interesting ways, and so it's really something that requires some thought. And as I point out on the slides, I think it also raises an interesting philosophical question. Given the way that mathematicians, informally just kind of infer what you mean when you say continuous or write down plus, whatever is going on mathematically, we have ways of supplying the relevant structure and inferring it. It's a miracle that mathematically we don't get into trouble more often. I mean, somehow mathematics as a practice, has ways of keeping it coherent. So I think we don't really understand that very well at all, how the mathematics works and how to control it formally. But this is something that I think we're learning as we develop the formal libraries.
Thank you.
There was a question from
Yeah, I think there was an online question by Andrew.
Yeah, hi, Jeremy. Actually, the previous question was one I was going to ask, but let me ask a related one. So, full disclosure, I'm not a Lean user. I'm a very keen user of Avigad, but the kind of things
That's okay.
kind of things you've been talking about, there are similar issues. So, what interests me, I'd like to ask, in Avigad, there's a really nasty problem for users. When it comes to the inference of inheritance of structures and so on, if you want to call it that way, it would be instanced arguments that you can go off the edge of a quadratic cliff, and your type checking will go from milliseconds to never coming back at all, as it were, for days, without the user being given much information about why that has suddenly happened. And I don't know whether that's the same in Lean or not.
So yeah, it is. Again, the complexity. So there are times when you're working on a file in development and things slow down to a crawl, and so people are always trying to track down these performance problems and so on. I'm not the expert here, so if you go to the Lean Zulip channel and raise this for discussion and ask questions, you'll have lots of people chiming in and so on. I think there are two ways you can try to deal with performance problems. And one is in the engineering of the underlying system. You just get the system to do things better. And the other one is in the engineering of the library, trying to restructure your library to avoid the problems. And both happen with Lean. So in the move from Lean 3 to Lean 4, one of the big innovations was a redesign of type class inference. So one way quadratic or even worse behavior arises is from like a prologue-like search, if you're just kind of back chaining and there are just too many paths. But now Lean type class inference uses more like a graph-like search. So it'll do memoization. So it's not as sensitive to cycles, and yeah, I mean, so it will cache information and avoid some of the problems that crop up. Another thing that Lean has long done is, when you're elaborating a term, it'll cache intermediate results. So if you have to infer the meaning of a plus, it remembers it while elaborating the term. And so if you have other pluses later on, it can find things more quickly. So I think I don't have a good answer to your question, other than that there are kind of various things that people do. But if you really wanted to get into a discussion of the nitty-gritty details, do come to the Lean Zulip channel, and experts come out of the woodwork and
no thanks.
Yeah.
But thank you for your answer. It's very interesting to hear the experience in Lean. I mean,
yeah.
My impression is that it's kind of very well engineered system.
Yeah, I think so.
I have one more question. Is this discussion is finished?
I think so.
Okay. I was just interested in your take on automation, Jeremy, because you had a slide with with the discussion on automation. So would you like to elaborate a bit about that? Do you think maybe some obstacles because of dependent theory or any?
Yeah. So I'm sorry, Angeliki, the sound in the room, it's a little bit muddy. So I heard most of it, but I think maybe not the keywords. So can you say again what the question
Yes,
is?
so it's not, it's more of a general question about your take on automation. So
On automation. Oh, yeah. Yeah, well, we need it. Again, this is something, so in the slides, I point out that, so what we have in Lean, we have a lot of very good domain-specific automation, a lot of small things. We have a good simplifier. The one thing we don't have is a sledgehammer like Isabel's. But one thing that I report on briefly in the slides is work by Josh Clune and Yicheng Qian and Alex Bentkamp that is getting us closer to having a sledgehammer. A lot of the challenge is, when you move from simple type theory to dependent type theory, as Sebastian's quote indicates, there are some extra challenges, but we're figuring out ways to address them. So in particular, Josh and Yicheng and Alex have written an analog of METIS for Lean that has special mechanisms that handle, that work in dependent type theory. So we have sort of a METIS for dependent type theory. And similarly, Lean has a monomorphization procedure to send things out to external tools. With dependent type theory, the expression's more complicated. It's harder, but Yicheng has done some really excellent work in kind of pre-processing and simplifying problems, kind of mediating between dependent type theory and the kinds of formats that external provers can handle. So yeah, so it's ongoing work, but I think we're making good progress. I'm hoping that we will have a workable sledgehammer for Lean, by the end of the summer. Yeah.
That would be really cool.
Yeah.
Thank you.